like to thank you for the opportunity to see Waterloo. I heard a lot about it and worked with people, and I was always impressed with it. And it's one part of Canada that I never saw, which was Toronto, which is like the major part of Canada. So I'm glad that I get a chance to see Toronto as well. And as I hear, this is always how the weather is, so I'm glad to experience the...
That's a secret.
Yeah. Yeah, just for... So anyway, can you hear me okay? Okay. So yeah, I'll talk about things that... I've done many different things in a sordid career, and I thought this might be of most interest to you. It's something that I worked on when I was at HP Labs, and I think it's being commercialized right now. The technology moved from HP to Applied Materials, who moved it to Germany. So, but I think it's an interesting thing because it's such got a lot of applications. You can do it in a university lab, and in fact, you can get very high resolution, much higher than optical lithography features. So if you're doing nano to giga kind of things, it's we literally had, if you can get the master, you can make things just with a little setup that big and get research quality stuff out of it. And so I thought it might be appropriate for you guys, and it's not that well known, and so I'd like to evangelize and point it out so that it goes somewhere. So the big motivation for this is, can we really print submicron scale mechanical, optical, or electronic structures in production scale quantities, not little onesies, twosies, or little tiny wafers, but really make lots of them. And what I've learned over the years, unfortunately, is electronic level reliabilities are often important. If you're going to make 1 million of something, it's not good enough for it to work 1 out of 100. And this really, it's not quite to electronic levels, but it's amazingly close for how little effort we put into it. So the, let's see, where's the top thing here? Oh, okay. So I'll just describe the imprint lithography. It's an older technology. I'll describe our version of it, which is self-aligned, which allows us to print over large areas and register layers. Talk a little bit about the equipment, and then some of the various results that we got. Electronics, we definitely got a lot of results. Some of the optical structures I can show a little bit, and this is more theoretical. I mean, but I just want to expand your ideas about what can be done with this technology. And so keep in mind that one of the advantages of this is that if you can make a master, which can come from electron beam lithography or come from nature, you can take a body part of an insect or something, anything that you can make a casting of, you can then replicate it. And one of the big problems, as you know, with electron beam lithography is it's great for tiny stuff, but you can't replicate it. So this is a process where you make the master and then replicate it. So be thinking of your favorite problem where you go, oh, it's too slow. Well, this might be a way through. So some of the motivation, there's all kinds of things, electron skins, photovoltaics, and we kind of emphasized large area, inexpensive, and flexible. And a lot of times we want 2 out of the 3 of those things. We are able to do things roll to roll, but you don't have to do roll to roll. You can do it on a wafer or other things. But anyway, there's lots of applications. I'm sure you guys know about those. Large area, if you have roll to roll, for example, you can handle flexible substrates where you don't have this kind of problem, and I'll show you that. But remember, you don't have to do roll-to-roll if you don't want to. It's just our particular implementation involved that. So that with the background, now I'd like to first describe imprint lithography and what it's about, and if it's a review, let me know. So the basic idea is that you make a master, and this master could be a silicon master. We made things on glass masters, and it has whatever structure you'd like to replicate. So it could be a electronic structure, optical structure, mechanical structure, whatever it is, you need to make that. And I saw lots of equipment that you guys have, so you can make these kinds of things. What you then do is make a Pdms stamp. Now, Pdms, for those who don't know, is sort of like contact material. It's rubber, silicon stuff, and it's an amazing thing. It makes a amazing replica. It can replicate actually little tiny 50 nanometer scallop features in a Bosch process. It's amazing fidelity. So you make a master, and then what we do is wrap it around a quartz cylinder. But you can also put it on a plate or all kinds of different things. But we wrapped it around a quartz cylinder. And then we had a roll-to-roll, which we had a Norlin 2P, which is a UV curing polymer. And we very precisely control the thickness. Using these optical filmetrics, we could control to fractions of 0.05 micron liquid levels. And then it's wrapped around this, and so this is an expansion. This is the tightly controlled fluid level. And right when the imprint is squeezing the fluid around, a UV polymerizes it, and so you end up with this polymerized, and then it releases at this point. Because the PDMS and the 2P are somewhat compliant, you can actually get what are called reentrant structures. We could literally make like mushroom tops. In other words, without ripping the top off. If you go slowly enough, you can actually make things that have overhangs if you want. So it releases, and you have this structure. And then whatever you want to do with this structure, it can be the actual material itself can be what you want, or we can use it as a mask. And I'll show you, we use it for a mask, but it can be the actual structure, or you can do other things with it. So, and please feel free to ask questions. Any feedback on or questions would be greatly welcome. So that's the basic imprint process. Now there are some things like squeeze film dynamics, which, as you're squeezing fluid out, I don't know if any of you have been on those things. For example, in the ocean, you have these boards and you go along, and if you go fast enough, you stay up, and then it slowly squeezes out. Or slipping in a bathroom shower, you have a squeeze film problem where if you're not heavy enough or whatever, so you can't push arbitrary amounts of fluid, arbitrary distances in the time of the roller, so you have to pay attention to that. It's not a big problem, but it's something you have to be aware of. And so when you see our structures, they'll look weird because they're kind of lattice-like. And the reason is that our average flow level is the same, so you don't have to squeeze fluid for long distances. If you try to squeeze too much fluid too long, you'll get a burp of a big chunk of fluid. But anyway, those things are all pretty well understood, what the time scale is and everything. Okay, so that's the basic. So where are you squeezing? Okay, so where we're squeezing is right in here, because this 2P has to reduce here and accumulate here. So imagine I had a high-level feature that was trying to push the fluid away, and then someplace else where it wants to go. If that's too far away, it won't ever get there, and then what will happen is the levels will be off. So you kind of design how far. So ironically, it's easier to make 2-micron features than 1 millimeter features with this. 1 millimeter feature, you'd have to squeeze. Yeah, you'd have to squeeze it. And we're talking about very precise height controls. In our particular thing, we have to control the heights to 1/10 of a micron or more. And so that's why it's more important for us. For other applications, it might not be important. Okay, so now that we've got the basic imprint process, how do we incorporate it into a process where we make, in this case, electronic devices, but it can also be mechanical. So it's kind of unique, and it greatly lowers the cost of manufacturing things. So conventionally, what you do is, if I want to make a electronic or MEMS device, and suppose I have 4 layers. Well, what you typically do is deposit the layer, you spin resist on it, align it, develop it, etch, strip clean, then you do the next layer, and you go around this cycle 4 times, and then you're done. What we do in this particular thing is we have the imprint step that I described earlier, but what we do now is we deposit all of the layers, and then we have one imprint step. And the various layer mask layers, suppose we had 4 mask layers here, the information is encoded in 4 different levels of the imprint polymer. So we sort of have, normally photolithography is a 0-1 operation. If there's no photoresist, you etch. If there is photoresist, you don't etch. Well, this we actually can have different levels, and using those levels, we can use that to have all the layer information imprinted in one step, and then we do the etching all in one step. And this has a bunch of advantages. One is that if the substrate changes size, which 50 micron polyimide will do, especially if it's meters long and you're changing the temperatures, all the things will change at the same rate and size, so we preserve alignment. The other thing is that we were able to bifurcate these things. This was done in Iowa. We could then send it to Palo Alto, do the imprint, and then do something here, etching. And so you don't need a clean room because it's all wrapped up and nice. And so you can really do modular kinds of development. So, there's 4 steps: the deposition, imprint, and etch. And so I'll go through the various parts. This is Iowa. This was, we worked with thin films. They make did make thin film solar cells. They actually had contracts with the Army to make flexible stuff or semi-flexible things. So here are, this was done in Iowa actually, and they do roll to roll. They would do it either on stainless, but ours were polyimide. And so here's the layers. We would do some metal layers, some silicon dioxide, silicon nitride, which will be the gate dielectrics. Then we have amorphous silicon, and then some N+, and then a top metal. So all these things are done in one location. They're done roll to roll. Actually, they were done on meter wide rolls, and then we would slit the rolls because our next steps could only handle 13 inches. Again, this is the imprint process, just to show you what kinds of things we could do. We can do, as you know, this was just with our flexible things. We could do 40 nanometer kinds of lines on 50 micron polyimide. Now, people can do with rigid things down to 10 nanometers or less. And you guys are probably familiar with some of those. And you can make very complex structures with multiple heights. And we could do this at roughly as fast as 5 meters per minute, which is quite a lot of, especially if it's 13 inches wide, it's quite a lot of devices. And one of the important points that's kind of here is that a speed of a device depends, the higher the mobility, the smaller the speed is shorter, so it's faster device. But it's even more dependent on the channel length. So if you can reduce the channel length, you can increase the speed much more than diddling around with exotic materials. So being able to make small transistors is really important for speed, if speed is one of the things you're interested in. A lot of the flexible applications that people are talking about, they're talking about, if you want Bluetooth or RF or something, you want to get small devices is more important than having some exotic material. This imprint lithography has a lot of advantages. It's high throughput. You can do small features, the self-alignment, which I'll get to, and so there's a lot of advantages over other ways of doing things. So it's not either or. In fact, one of the ideas is to combine inkjet with imprint or imprint with photolithography. In fact, for a while, I don't know if it's still true, but imprint lithography was on the roadmap for high next generation crystalline silicon. Why? Because you can beat the optical limit of in a high throughput thing. So if you can make some of the electron beam lithography, you could use imprint. So there's a lot of reasons why people are interested in it. Sure.
Because you have, as you shown in the previous slide, you have different kind of materials, silicon nitride, silicon oxide, metal,
right.
So how do you want to solve that?
Well, so I'll show you for our particular thing how we solve that. Partly the resist helps protect you for the different ones. And so I'll show you how obviously when you use a metal, we use wet etching. And so I'll kind of maybe show you some of that. And you see, so we have wet etching. It isn't, now one thing I can say is the self-aligned process is not as versatile as unrestricted photolithography. In other words, what you're saying is that's correct, that we have constraints placed on selectivities. You can't do arbitrary things against arbitrary things. We can't make arbitrary structures. There are limits if you want the self-aligned. If you have some other way of aligning, which the things we use just on the lab bench where we're not doing roll-to-roll and sort of quickie experiments, we just would imprint things, and there it's more like an alignment problem. So if you have however well you can align your different imprints, and because you don't have a flexible substrate, you can do more alignment kinds of things. Then you can do whatever you do with photolithography. So we're kind of going the specialized route that because we're on flexible, we have problems that restrict what we can do. But keep in mind, you could do it like photolithography, and then you wouldn't have these constraints. But it's a good point that there are constraints, and you'll probably see that. So the problem with a flexible substrate is that if we suppose we want to make a transistor with a gate, some sort of semiconductor and a source drain, these need to be aligned to roughly half a micron or 0.2 microns, this gap with this metal. And normally use different masks, and you mask align it, and you can get that alignment. But if the substrate changes size when you do the different things, things won't line up, and you got a big problem, because it literally, polyimide will change millimeters in size, and so your gate would be nowhere near the source drain. So what we do is we encode the different information in different heights, and I'll go into more detail, but everything deforms, and it deforms uniformly, even though this deformation is actually inhomogeneous. It's not like it just is an affine translation. You know, some places where the metal is bigger, it kind of has a different expansion, and so it's actually a nonlinear kind of thing. This is how the self-aligned process, and this is kind of our contribution to the whole thing, as well as just getting things to work. But you start with the stack of materials. This was done, again, all in one go-round, wrapped up, sent through FedEx or whatever. And then we get the thing, we clean it off, and then do an imprint. So you notice there's a bunch of different levels. There's 0, 1, 2, and 3 for this. So what happens is we now etch down, and so we etch away all but the lowest level, which in this case is the gate metal. We then etch away the that metal and pattern it. Okay, then we undercut. So we've now undercut right through here. So now these pads are isolated. The gate pad, the source, and drain pads are isolated from each other. We now lower the level. So we now bring the, we're using the level information now. So we've now uncovered this. So we can now work on this. But the rest of it is still more or less covered. I mean, you will have some little undercuts. And that kind of limits, for our imprint lithography, what kind of spatial resolutions. It depends on how controlled your undercut is. But anyway, so now that the gate pad is, now you can expose that. Now we do another lowering, and so we've now exposed the channel region. So we can now etch the N plus away, and the gate, I'm sorry, not the N plus, but the gate insulator, and not the gate insulator, but the N plus. And now we have still the source drain here protected by that. And then we remove that, and we now have a completed transistor. And we can also do more complicated things. This is now, it's not just enough to make a transistor, you want to make arrays of things. So this is the same process for arrays, where we now have a pixel capacitor. Here's our transistors. We also have crossovers and other things. Now, the reason for these kind of grill-like structures is that we have to undercut in order to remove a layer. So these have to be thin enough so we have controlled undercut. Now, so you'll see that this is sort of the same kind of thing. We do that, we do this, we expose this, and we go through the various things, and we now have a completed backplane. So it's this can be now part of a MEMS device, or we can control for a liquid crystal display. I'll show you we've incorporated an electrophoretic and OLED kinds of things. And it's basically an arrayed, active matrix addressed array of metal plates that we can change the voltage on, and you can use it for whatever you want. Yeah.
How much control of the undercut do you need for this?
Not very much, because you just need to make sure that it undercuts here, but doesn't undercut here. And so
your tolerance is what, like 10%?
Yeah, I mean, you don't want to make sure that this gets completed, but this doesn't go. So it's you can make whatever ratio you want. You know, if this is 100 to 1 or...
Just design around that.
Yeah, you can design it however you want, you know, subject to other constraints. And again, this is only if you want to use imprint lithography for flexible stuff and you want very high complexity circuits. And then this just shows you what the different layers are as patterns. I'm stripping away each one so you see how there's a gap here in this one, and there's a continuous metal, and there's the bottom gate metal. So what does the actual equipment look like? Here is the imprinter. We designed it. We worked a little with Conseco, a Japanese company that just dealt with, I think it's tapes, but we just gave the designs. We first had a 4-inch one, and then we have a 13-inch one. This is the house-built, more 4-inch one. You can see it's got some rollers and the UV in here, and then a take-up roller. And here's what the quartz roller with a mask around it looks like. And then this is a 4-inch sample with the aluminized mylar. Well, it actually has sputtered stainless steel on the back, partly for static buildup for this case. And then this is the imprinted pattern. Now, if you just want to goof around with stuff, you can make a pattern, and we just had a imprint come down, and we just had an air bladder that just kind of provided the force, and it kind of starts from the center and squeezes things out from the center. And we did all kinds of things so you don't even need this kind of stuff to do stuff in a university setting. You can just take your thing, make a PDMS master, and then use this bladder to kind of get so you squeeze stuff out from the center so you don't trap stuff in the middle. Or you can do a roller kind of thing. Some people have can put it on a roller and then just kind of roll it out and do the imprint lithography there. And again, if you can do your alignment, then you can just treat it like a mask in a photoresist mask and do what you normally do. But it can be at nanometer type scales if you want. And you can do very precise height controls on things. See here, this is, I don't know if you can see, but we made a master using a Bosch process where you etch for a little bit, then you passivate and etch. And you see there's little scallops here. Each one of these are 50 nanometer scallops, and they all get replicated. And you notice the top is actually a little bit bigger so that's that reentrant thing. So you can make very complicated structures, and the fidelity of replication is very high. So if you want an optical structure or a flow structure or something like that. Now, it's really suited for optical. Now, flow structures, often you'd probably want like 100 micron things because the impedance of flowing fluids through too small a channel start getting high. I mean, electrophoretic can help you, but so the 1 micron to 10 microns are pretty easy. 100 microns, if you have thicker things, which you tend to want for flow, you can do that. But anyway. Okay, so now here's something about the etchers. Again, you don't need this. This is more a function because we have roll-to-roll. We had wet etchers where things would go unwound and would go through a bath and then come out. We had a water knife so we had very precise timing of how long it was etching for, and then you shut the etching off because you don't want it to keep going, and that would go into the water knife would kind of stop the etching, and then you'd do a rinse, and then you'd have a dryer, and you could do various. We actually had multiple stations. This was partly designed by us, but mostly by this company that does this kind of thing. But again, you don't need any of this just for what you want. So, and then we had dry etching. This kind of addresses your issue about etch selectivity. So we have both wet and dry etching. So for metals, we use the wet etching, and for dry etching, we did the. So there's a roll-to-roll here, and this we made, and it's big enough to crawl into actually, but and that's the plasma in the thing. But it kind of shows you how it works. Here's some of the structures that we made. And you notice this characteristic waffle. That's because we want the average height to be constant, so you're not squeezing fluid around. And these are different transistors. You can see that's 2 microns right there, and so you can see how accurate kinds of structures we can do. Here's some transistors. These are amorphous silicon, and this is the source drain current divided by W over L. So ideally, if there weren't short channel effects, these things would be all on top of each other, which they are for the 100 micron, 50 micron. When you start getting to 2 and 1 micron, you start getting short channel effects, not so much short channel, but contact effects. And so that's why the current isn't quite as high as you might expect. But anyway, these are quite good transistors, particularly like if you're at the 5 micron. Remember, because you're dividing by W over L, which is 20, so we're actually getting 20 microamps out, which is pretty good for amorphous. And it's partly because you got a small device. And remember, we're doing it over 13 inches. And you can get, decent mobilities of almost 1 and very low off currents in general. Now, we've also done it with zinc tin oxide, so metal oxides. It does require working out the chemistry a little bit. But yeah, this one we had ITO contacts and zinc tin oxide. That HP actually has a lot of intellectual property in the metal oxides. We filed a patent at the same time Hosanno filed, and somehow ours got granted and his didn't, which is amazing. So anyway, it was partly through Oregon State, but anyway, and hafnium oxide dielectrics. And so we did those, made those kind of transistors, and of course, they're way better than amorphous silicon. I mean, you can see that the amount of current is quite a bit higher. This is a device, you notice this characteristic weird structure, but this was not so much for flow isolation, but also, for flow leveling. But so we can get mobilities of 10 to 20 on the zinc tin oxide, and IGZO, I think we get even better, but here's the full zinc tin oxide, the capacitor, the transistor, the gate line, and crossovers. So we can do some pretty high performance things. There are, as you know, with everything, there's instabilities. The metal oxide transistors are remarkably stable for most circumstances, except a negative bias with light, and you get this instability that kind of comes back. But people kind of understand that, and so they have been able to deal with that. That's why metal oxide transistors are being used, can be used for drive electronics, although I guess people are going to laser annealed poly as the preferred thing, but you can make things that are fast enough for either at least driving the gate drivers and bigger displays. Bigger displays, the pixel time starts becoming faster than amorphous. So if you have 4K display that's 80 inches, the time scale for switching that, there's too much capacitance, so you start needing metal oxide for the active matrix thing. Here's, since I know some people are talking about having to deal with metastability, this is how the threshold voltage shifts for amorphous silicon, and this is for the ZIO and some of the others. It's, it's less, but and it requires light. So if you keep light off of it, here's actual displays that we made. So they're actually flexible. The only reason it's in this big bulky thing is contacting flexible things, many thousands of lines. So we have, I forget what exactly the line count on this is, but we had to make a whole bunch of, so we basically brute forced it to have a bunch of little solder bumps that just are mashed into it. And that's the only reason we have that, is to make that. Here, I don't know if this is going to work or not. Usually AV doesn't work, but we'll see. Oh, okay, so you can actually see it work. So this is an e-ink front plane. And I don't know where we get these corny things. Anyway, you can see that it's working with thousands of pixels all working. And as you know, if you try to do this with inkjet and getting enough things working is pretty hard, where this, could actually, we literally have meters of material. The hardest part was actually testing. We didn't have roll-to-roll testing of the stuff. But anyway, that's electrophoretic. Here's high-resolution displays that we made. 120K pixels delivered. Then we also did OLED displays, so that requires a 2-transistor circuit. So this is what the mask layout is. This is the functional layout. The only thing that's a little interesting is this, how to get a signal from the bottom layer to the top layer. We use this capacitance structure, so it won't pass DC, but it will pass an AC signal, and that's good enough to switch. This, we have a little trouble on, well, anyway, this is the OLED kind of display, and then we put color filters on it. By the way, one of the leading applications for imprint lithography is just making color filters. In other words, you use the imprint to make little cups that are very precisely aligned, and then you just shoot with inkjet into the cup. And your inkjet isn't so accurate, but the cup repositions it, so you get very accurate levels. And so people are using it for that, or also touchscreen displays, or wire polarizers are all things they're using imprint for. So anyway, here's the OLED display. Now, there's bad pixels because to make the contact, we had to put something on with an anisotropic kind of conductor, and the OLED, it's kind of punctured through the OLED stuff a little bit, but let's see. I don't know if this one, anyway. And none of this was done in a clean room, by the way. So.
There's this single wavelength OLED emitter and then color filters on top.
Yeah.
Did you do this with emissive?
Yeah, if you can jet the emissive material, yeah.
No, I'm talking about like using the sale process to etch. Or
it's hard to etch organics because your mask is organic and your OLED is organic, so that's a little tricky there. Anyway, we estimate the costs are a lot less because all this stuff you don't need a clean room. You just put the roll-to-roll in a clean environment, and then we found that even air infiltration in one of these things is very slow on the sides. So you probably don't need anyway, we estimated it would be an order of magnitude lower in costs. And particularly for the larger area stuff, because the larger area stuff are getting unreal. I toured the AMAT thing. They have a cluster tool. Oops, I just blew it, I think. They have a cluster tool that's so big they can't even assemble it in their factory. They have to ship it to wherever it is. You know, it's the Gen 10. It's 3,500 millimeter by 2,500 millimeter. It's almost the size of a double garage door glass that's 2 or 3 millimeters thick, and they're shooting this glass around, and they can't even ship the glass. They have to make a glass factory right near the fabrication, because most freeway underpasses aren't big enough for the glass trucks to move through, and so it's getting pretty wild. But with roll-to-roll, you can easily make, at least in one dimension, you know, arbitrary lengths of stuff. So remaining hurdles like roll-to-roll testing, what are the flexible substrates, particles, you know, controlling them and always yield, you know, those are kinds of things. But the other thing is just what all you can use it for, and that's where you guys can come in with whatever ideas you have. So those are electrical things. I'd like to show you some of the optical things, but maybe I should hold up for some questions. If that's, yeah.
Well, a quick question. How do you dissolve the masking layer? That's not the post process?
No, we use a dry etching process.
Okay. Isn't
Yeah.
that a rate limiting step?
It's roll to roll, so it's, you know, we have the speed and whatever, and we can design the time scale. And you're only etching about 0.2, 0.3 microns of a polymer at each step.
Okay. Yeah,
So
I normally think of that as being a very slow process.
well, if you put oxygen in it, it ashes it, or it can accelerate it.
Right, yeah.
It's, you know, a lot of chemistry there, and you're getting out of my expertise, but, you know, chemists can do amazing things, so. better living through chemistry, right?
Okay,
Yeah.
following up on that one, do you see any rounding of the features as you do this lowering of the levels, or it's actually you manage to do it razor sharp?
Well, there's a little bit, you know, it's not completely anisotropic, so there is a little shrinkage down. That's sort of in the 0.1, 0.2 microns. So for our particular thing, I wouldn't claim that we do better than about 0.1, 0.2 microns, partly the undercut parts of things. If you don't do the self-aligned part, but do the other things, you can do much better than that. So you can do 10 nanometer kinds of features if you don't do the self-aligned part. Yeah.
So you have shown an image of the high aspect ratio features, like
Uh-huh.
process, right? So I believe
Yeah.
that's made in PDMs.
Well, it was made in like SiO2 and silicon, and then we just cast it. So we
Do you experience any collapsing of the high aspect ratio features of PDMs, like collapsing with each other due to surface energy?
what we have observed are if it's too floppy of a structure, they can kind of come together, or you know, you can get you know, where it's kind of flops and then you get stiction together. Although one group at HP Labs turned that into sort of a feature. I don't know if you've heard of surface enhanced Raman scattering, but we made these pillars that when after the water or the dissolving etching defined, they would collapse together and right in the middle you could put a a particle that had the thing you wanted to do, surface enhanced Raman, and we got enhancement factors of 10 to the 9th. Controllable, you know, because you get very high field enhancement. And so a whole business went off, like we made these structures where they'd get the 4 fingers to come together and you could put molecules in there. And normally Raman scattering, you know, is like 1 part in 10 to the 7th. So you need photon counting and photomultiplier tubes and all kinds of stuff. But we were able to make little chip little inserts, you know, disposable things that you'd put the, they were after melamine, that was, you know, being added to milk for a while, as a showcase thing, and they could get enough signal with just handheld stuff. The idea was to make a Raman scattering, portable Raman scattering, because as you know, Raman scattering is and somewhat more versatile at doing molecular identification. And so if you could do that. So.
And for roll to roll, you make your master molds by wrapping the Pdms film around PARC.
Right.
Then I would expect a seam problem, right? There would be a seam there.
There is a seam. We make it between displays. It depends on the size of the roller and what you want. Yeah, you can't, you know, so if you wanted it to be this wide, you make the quartz roller, you know, wide enough that the seam would be at the edge, you know. There might be ways of shimming it. You know, that seems a lot harder than just making a big round thing. Yeah. Okay, so now this was something that got spun out. I don't think it currently is being done with roll-to-roll, but we definitely did some demonstration things with it. This is an optical thing. So the idea is that if you want to make a like glasses-free 3D, what you want to do is not only control the intensity at a pixel, but the direction of light at a pixel. And so what you basically do is take a pixel and break it up into 64, 8 by 8, and each one of these is a grating that sends light out in a different angle. And so you send the light in, and then it gets grating coupled out, and use liquid crystal displays. And these structures can be made with Imprint Lithography, and you can get glasses-free kind of 3D displays. Right now, they're doing it not with Imprint, but with photolithography, so they're combining it to small things. So they're thinking of more for glasses or for logos, you know, to be cool. Instead of the Apple, they'd have an HP logo that's 3D or something like that. But this is just to stimulate your guys' thinking about optical structures, because it's very compatible with optical kinds of things. And this can be made directly with the 2P could be this material or some other imprint thing, or you could pattern it into SiO2 or some other thing.
So this thing actually is active in a way that you can steer the light, or it's just basically?
Well, you basically turn on this liquid crystal. So imagine a very high resolution liquid crystal display, and 1 out of 64 turns on and sends the light out that way. Or I suppose you could, you know, multiplex. You wanted this person to see one thing and that one to see another. You could actually do that kind of thing. But it's a way to get angle as well as intensity at each point. So it's not, you know, you're not going to get the highest resolution because you're down by a factor of 8 in each direction. But it's pretty neat. I mean, you just see things. And again, you know, if you're too close or too far, it won't work. But there's a viewing volume that's pretty nice, and you can get color and everything. Now, another thing that I filed some patents on, although I don't know quite what, is Gecko Self-Cleaning. So again, I'm just trying to get you guys interested in thinking beyond the box or whatever, or beyond the hoof or whatever, or foot. So Gecko, as you know, they can climb on glass. They can climb upside down. And for the longest time, they wondered how they do it. Do they suck? Do they have a vacuum? They put geckos in, or at least feet of geckos in vacuum, and it still worked. And they finally figured out that what it is van der Waals force. And so there's enough force. It's not a super strong force, but it's amazing in that the amazing thing about Gecko is not that it can stick upside down. I could get, like 3M has all kinds of adhesives that I could hang even my weight upside down, but I couldn't remove it. And if I started walking up a wall, it would get so impregnated with dirt that halfway up I'd fall off. The amazing thing about Gecko stuff is it's a self-cleaning dry adhesive. So how does it work? Basically what it's got is this hierarchy of little surfaces that allows you to get huge contact areas regardless of what the surface topology is. So how does it do it? First of all, it's got 4 different feet. So if there's a gross level, it can accommodate it by that. And it's got 5 fingers, which can accommodate different heights. And then on each of those fingers are these ridges of things that have hairs. And then on each one of these, there's 1,000 little branches on top of that. And on top of each one of those are little kind of spatulas. They call them setae. So you can get huge contact areas. It's sort of like a fluid. And the important thing is that the bending force is not very high. Because if it took too much to bend something, and then the van der Waals attraction wasn't very great, you would end up, it would be pushing off. So this is like a fluid in that it's very low energy in bending to get this to get high contact. And it gets high contact. So you get this very high contact surface that has huge amount of surface area. It costs almost no energy to get that contact. And then you have van der Waals force. Now van der Waals force is interesting compared to normal like gum or some sticky force in that, suppose I have a ball of dirt. It will stick to the gecko's foot because there's a van der Waals force. It will also stick to the substrate. So suppose a gecko puts his foot in sand or some dirt. Now it puts his foot onto a surface. Well, that particle will feel just as strong a force between the dirt and the surface and the dirt and the gecko's foot. So each time it puts its foot down, it'll lose roughly half the particles. So they've done experiments where they put it in polystyrene spheres or something. After 8 or 9 times, the sticks and comes back. And so because of the symmetry, it's a self-cleaning adhesive and allows you to create this thing that you can climb walls. Because, like I said, I could have, something and I'd get halfway up the wall and there'd be so much dirt in it, I would just fall off. But this, it doesn't happen that way. And so what does that have to do with imprint lithography? Well, we can make things like this because some of the scales are similar. So this is one concept where you start with a substrate that has a bunch of fibers. You make this in a giant block. You put a whole bunch of fibers together and then slice it so you have some fibers. And then you do imprint lithography, or you can do polystyrene spheres and various things to get the different levels of structure. So you have some compliant large-scale structures and you have smaller compliant things on top of that. And so you can make a kind of this hierarchical compliant structures, for example. And because you can do this in roll-to-roll or very big things and flexible, it can accommodate the macroscopic disparities, and you get this kind of structures. And anyway, that's the kind of thing that you could think of. So I'm just trying to get you guys excited about what things can be done. Anyway, I hope I've got you interested in imprint lithography. And again, you can combine it with your existing stuff. Like if you have photolithography, you can do, maybe you need a step where you need electron beam lithography, and it's too expensive or parallel. You can have the mask done and make a casting and then do processing. You can combine it with inkjet. You can combine it with other things. And you can really make thousands of devices consisting of thousands of transistors, and they work. And they're high performance because they're micron size things, not, we do a lot of inkjet printing of stuff, and you have 20 micron channels or really big sloppy things. And for some applications that's fine, but this is pretty good. So I think there's a lot of applications, and thanks for your attention. That's all.
Any questions for one? Talks that you don't have?
Yes. So how good are your nano-imprinted detail thing?
Well, we haven't gotten super far on that. Some people have gotten where they claim they can. Now they didn't use imprint, but there are some people with electron beam stuff have gotten stuff that if they scaled it up to that big would be able to hold you for a little while. So you can get around, I think it's something like 90 newtons per centimeter squared, or there's some number like that I'm forgetting now. That's roughly the amount of force you can get ideally, and then of course geckos tend to be a factor of 3 or 4 below that. But yeah, so the idea is eventually you could climb up El Capitan with your.
A few years back, there was a science paper.
Yeah.
Gecko Self-Cleaning created this.
Yeah. Yeah.
So what's the 5 meter per minute? What's the limit? Why that?
Well, what starts happening is you have to release the polymerized polymer. If you go too fast, you start tearing chunks of the PDMS mask out. It doesn't release fast enough. And one of the questions you might ask is, well, how many imprints do you get? Because if you only get one, then that's kind of a waste of time. And we've been able to get thousands of imprints. Often it's not so much the wear as the polymer starts swelling a little bit because of the solvents and stuff. And so the dimensions start changing a little bit. That's
So the faster you go, that
the more likely. But there's a whole bunch of chemistry to be done there, making more resilient polymers. And we had techniques for oxygen hardening the surface of the imprint polymer, so it was had a surface hardness. So there's lots of tricks to be played there. But the beauty is you can make many castings too. So even if you have a couple thousand, you can get from one master, you can get many copies. So, but yeah, it was mostly the wear that determined, and that partly depends on the aspect ratio. If it's shallow little thing, you can release it better. If it's a deep thing with bad aspect ratio, especially the mushroom tops, you have to go pretty slow. Otherwise, you'll end up with a mushroom top caught into your thing. Yeah.
So think about when you showed the TFT and the arrays where you have to do multiple height levels. So do you do one imprint step or do you
Yeah,
do multiple?
just one, yeah. And there's many different heights. So that's the non-obvious part of it, is that you can encode 4 different masking layers with 4 different height levels. And you're actually able to do stuff. That way everything changes size and everything's still aligned. So that's self-aligned part of it. So
So when you do the undercutting of the metal to isolate the gate from the substrate side, and then I think in your diagram when you showed the undercutting side, you still have the imprint mask covering the
right.
channel.
Yeah. At one point, we have sort of like a freeway overpass where we've, if you look at a mask and a structure, there's some place where it's sort of like you need to pull the tablecloth out from under stuff, and undercut is how we do it. You need to remove a metal layer without the overlayers, and so we do it by undercutting.
And then you do dry etching, use dry etching to expose the channel area so that you can etch the NPM plus.
Yeah, so dry etching is for the non-metal things, and the undercut, of course, is wet etching.
So
Yeah.
I was curious, you mentioned that you can actually imprint overhangs. It doesn't have to be like pyramidal.
Right.
Is there any use for it, or just curiosity sort of thing?
Well, we had this one thing we were making atomic scale resolution storage at HP, and one of the things there is if you have an overhang, you can get, and you deposit a layer, there'll be a gap, and so you can get isolation without patterning. If you can, we would purposely make a photoresist that had one photoresist that was more etchable and another harder one, so it's kind of undercut, and we would get that kind of overhang. And then you deposit a layer on top of that that's not as high, so imagine you have a kind of a thing like this. Now, if I deposit with something sort of directional, I'll end up with something here and something here. And these are not connected anymore. So if I want to isolate this metal from this metal, this is a way to do it. So there are uses for that kind of.
But okay, so obviously there are uses for that, but not necessarily in this step, of using the mask only to lower the level edge, and you add the deposition process on the top of that.
Yeah, but you can imagine we want to put a transistor here or something here. We could actually incorporate that into our process. But yeah, so there are definitely applications for that. Or there's interesting optical things, like if you want, this to only certain angles light comes in, for example. So. Oh yeah, that's a good one. Yeah. Yeah, and by the way, that's another application is you can make those hyper hydrophobic surfaces with making little structures. And again, it's really suited for that because you can. There, a few defects doesn't kill you, and you can really do meters of the stuff. In fact, I had one patent idea was, Gore-Tex normally has holes that allow vapor to go through but not water. Well, under heavy rain conditions, it kind of, you get so much fluid there that the vapor can't get out, and so you start building up steam. Well, I thought, I could put a hyper hydrophobic, put hairs out there, keep the drops away, and allow the water vapor to come out. So you have this hybrid Gore-Tex kind of thing. So.
Very good. Let's thanks Warren again.
Okay, thanks.